Hey everyone, and welcome. If you're a physics student who's ever felt completely overwhelmed trying to grasp mechanics of the incredibly small, you are in exactly the right place. Welcome to today's explainer. We're taking the highly abstract, honestly mind-bending world of quantum mechanics and translating it into a straightforward, easy-to-digest study guide. We're going to break down the actual science, but leave the dense jargon at the door.
All right, let's just jump right into the syllabus for today. We'll be covering the quantum revolution, superposition, the uncertainty principle, wave-particle duality, and we'll wrap it all up with the infamous double-slit experiment. Starting off with Section 1, the quantum revolution. Let's set the stage by looking at exactly why Newtonian classical physics completely failed when it came to explaining the atom. To understand why this revolution even happened, we have to rewind to the early 20th century. See, according to classical physics, an electron orbiting a nucleus should just constantly radiate energy and, well, crash right into the nucleus. But atoms obviously don't just collapse. So in 1913, Niels Bohr hypothesized that electrons actually exist in special quantized orbits. Then, fast forward to 1924, and Louis de Broglie takes a massive leap. He proposed that if orbits are quantized, maybe particles like electrons are actually behaving as waves. This realization led Erwin Schrödinger in 1926 to develop his famous wave equation, and literally just a year later, Werner Heisenberg formulated his uncertainty principle. It's absolutely wild how rapidly physics shifted here, moving from rigid classical models straight into these fluid wave-based models, spearheaded by Bohr and Heisenberg.
Now, because of this math, we had to completely rethink what an atom looks like. Instead of those neat, circular, planet-like orbits you always see in basic textbooks, electrons actually exist in these complex, three-dimensional probability clouds. We call them wave packets. They don't really have a single distinct location. They just exist as a mathematical probability of being found in a particular area.
Let's move right along to Section 2, our first core concept, superposition. This is where our classical intuition starts to really break down. So, if particles are actually waves of probability, how do they exist before we look at them? Well, that brings us to superposition. This is the principle that a tiny quantum particle exists in a combination of multiple possible states simultaneously, until it's measured. The crucial thing to understand here is that it's not just about us being ignorant of the particle's state or our tools not being good enough. The math tells us the particle is literally in a combination of all available states at once.
I know, it sounds totally impossible to wrap your head around. But to visualize it, picture a quarter spinning really fast on a smooth table. While it's rotating, all you see is a silvery blur. If I ask you right then, hey, which face is pointing up, heads or tails, what would you say?
You couldn't answer, right? Because exactly like that spinning coin, the quantum state is occupying a state that's neither heads nor tails, but a combination of both. It genuinely hasn't settled yet. It's only by slapping your hand down on the table, which is the equivalent of making a measurement in the quantum world, that the coin finally collapses into a definite state, choosing heads or tails.
All right, on to Section 3, concept number 2, the uncertainty principle. Let's see how this all connects.
Formulated by Werner Heisenberg, the uncertainty principle states that you literally cannot simultaneously know exactly where a particle is and exactly how fast it's going. Because everything at the quantum level is fundamentally a wave, the universe itself enforces a strict mathematical trade-off. This isn't some glitch in our lab equipment. It is a fundamental, unavoidable property of nature.
Think of it kind of like a ripple in a pond. To figure out the exact speed or momentum of a wave, you have to measure a long stretch of peaks and troughs over a distance. But because that wave is spread out over space, you completely lose its exact pinpoint position. On the flip side, if you perfectly localize a particle to find its exact position by zooming in on just one tiny peak, you lose all the information about its wave frequency, and boom, you lose all knowledge of its momentum. The more you nail down one property, the less you know about the other.
Moving to Section 4. Concept 3, wave-particle duality. Let's talk about why we don't see this bizarre stuff happening in everyday life.
Now, you're probably wondering, if everything behaves like a wave, why doesn't a tennis ball act like one? Well, here's the secret. It actually does. Everything has a wavelength, but for large, everyday objects, the momentum is so massive compared to Planck's constant that the resulting wave becomes impossibly tiny. For example, a tennis ball moving at 10 meters per second has a wavelength of 10 to the negative 33 meters. That is literally less than the width of a single proton. It's completely undetectable. Compare that to a tiny low-mass electron, where the wave behavior is spread out and absolutely undeniable.
And finally, Section 5, the double-slit experiment. Let's put all of this together with the most famous proof in all of quantum physics. Imagine shooting tiny classical marbles through a barrier that has two slits cut into it. You'd obviously expect to see two distinct bands on the wall behind it, right? But when physicists do this with quantum particles like electrons, shooting them one by one, they do not get two bands. Instead, the particles act like rippling waves. A single particle goes through both slits at the exact same time in a state of superposition, interferes with itself, and creates this complex, striped interference pattern on the back wall. It's crazy.
But here is where it gets truly fascinating. What happens if we try to cheat? If you place a detector right at the slits to figure out exactly which slit the particle is passing through, the interference pattern immediately vanishes. The wave function collapses. Just because you measured it, the particle goes right back to acting like a solid classical marble and gives you two boring bands on the wall.
And we know this for sure because we test it constantly. In modern labs today, physicists use tools like Mach-Zehnder interferometers, bouncing particles through beam splitters and detectors, proving time and time again that the mere act of observation physically alters the quantum system. You simply cannot observe the system without changing its fundamental behavior. So as you review this study guide, I'm going to leave you with this mind-bending question to chew on. If particles change their fundamental behavior from waves to solids just because we measure them, what does it actually say about the very fabric of reality itself? It turns out in the quantum realm, just asking the question changes the answer. Keep questioning the universe, guys, and thanks so much for joining me on this explainer.